So, Bismillahirrahmanirrahim. Assalamu alaikum. In this video, we'll analyze the soil structure interaction through the PLAXIS software. So, for that, we'll try to understand it by solving an example through PLAXIS software. So, an example of building that is subjected to an earthquake. So, building is consisting of 4 floors and 1 basement that is 2 meter deep. And the total height from the ground level is 12 meter. The total load of the building is 5 kilonewton per meter square. So we'll model this thing in the PLAXIS software. So let's go to the PLAXIS software. Yes, it's a new project. Okay, we'll give it a title of earthquake seismic analysis, seismic soil structure interaction. Now we can model it as plane strain model, 50 noded element, and yes, we have to change the time in seconds as time of earthquake is very short. It is in second, so we have to change this one. 150, leave it as it is, spacing is 1, and okay. Now I'll start from here, and in the horizontal direction I will go in 100 meter. We'll click over here. As the subsoil layer thickness is 20 meter below the building, so that is why the thickness is 20 meter. Just we'll click over here, and yes, the geometry of subsoil layer is created. Now we have to model the building by plate element. So it's 4-story building with 1 basement, so I'll select the basement plate element. So we'll start from here. Yes, and I will go towards the 32 meter from the ground surface, starting from 22 meter. It's 6 meter wide. Yes, we'll go down straight. Now as there is a basement of 2 meter deep, so I will go from here downward 2 meter down. We'll click over here, and then click over here, and we'll finish over here. So this is how I have modeled the plate elements of 12 meter just above the ground surface. Now I have to define the floors as by the, just to separate the basement. Yes, it's a beam element, you can say beam element. Now the next is at the 3 meter from this, so from here is the 3 meter height. Yes, I can zoom in as well, just to make the better understanding of it. Okay, now I will click the plate element again. Now I have to go 3 meters above as well, from 23 to 26. Yes, over here. Yes, now from 26 to 29. I have to go 29. From here it is 29, basically here. So now you can see this is the basement of 2 meter deep. This is 3 meter, 4 floors, 3 meter each height of each floor is 3 meter. So now I'll go back to zoom out just to work. Now the next step is to provide the standard fixed T's. Yes, Now I have provided the standard fixed. Now what I have to do is to define the material properties. So for the material properties, are the subsoil layer are some. We'll go here, go to the new, it says subsoil layer. As the Mohr-Coulomb model will be used, or we can model it as elastic model. So we'll select the linear elastic model. Soil will behave like linear elastic due to the earthquake. So the next thing is drain condition, as it's a soft soil, sandy soil, so that is why the condition is drained. The unit weight is 17 unsaturated and 20 is the saturated unit weight. And we can provide the permeability as well. So go to the parameters. Will not define the permeability as there is no water, so it doesn't matter we define or not. Elasticity modulus is 30,000. So 30,000 is the elasticity modulus, and the Poisson's ratio is 0.2. Now it has automatically calculated the alternatives, that is shear wave velocity, primary wave velocity, and as these are the parameters for the seismic analysis, these related to the earth, motion of earth, motion of waves in the earth. So I'll change the color, we'll make it as it is. Okay, now the subsoil layer has been defined. Now I'll go to the plate. We'll define the plate element properties. So beam slabs are plate, beams elastic, and we'll see what are the properties. Now the material model properties, and the normal stiffness is 5 into 10 raised to power 6. (9,000) is the flexural rigidity. And weight, here we'll put the weight of total building weight, that is 5 kilonewton meter. So here we'll put the 5 value. Now the Rayleigh coefficients, will have to put the Rayleigh coefficients. These are given in the table, that alpha and beta are 0.01, 0.01, and beta both are given 0.01. Okay, now we have to move towards the soil, as we have defined this as elastic, so we have to define the Rayleigh coefficients as well for this, so that are given here as well. You can see Rayleigh coefficients for the subsoil layer, that is 0.01. So we'll click 0.01 over here for subsoil layer. Yes, okay. Now the properties have been defined. We will have to assign the subsoil, select and drag over here. Now for the creation of mesh, we have to assign the clusters, these empty clusters with the soil. After while performing the calculations or initial stresses, we will deactivate these clusters of in the meanwhile, to generate the mesh, we have to assign the soil properties to these clusters, just for the easiness to create the mesh. That is why we are assigning the material properties to these clusters like this. Okay, now we'll go to the plate element. that is beam. We'll select and we'll drag to the beam elements. Now these have been selected. This one is selected. The beam properties have been assigned to the plate elements one by one. You can see here. So this is how we have assigned the properties of the building and subsoil. Now the next step is to define the prescribed displacement of the base. So what we'll do here, we'll go to here, prescribed displacement from this in this. Now it will be in horizontal direction. We'll select and we'll define its magnitude. Prescribed displacement. There is no displacement in the vertical direction. We'll keep it as 0, 0, and this will be 0.01 in the x direction, horizontal direction, positive in the rightward direction. So you can see prescribed displacement has been assigned at the base. Now we have to assign the boundaries, the special boundaries of earthquake. So we'll go to the loads and standard earthquake boundaries will be assigned. So you can see these are the standard boundaries for the earthquake. We have to assign these as well. So the next step is to generate the mesh. We'll generate the mesh. Yes, the mesh has been generated. Okay. Now for the initial conditions. Okay. As there is no water present, we'll not consider the pore pressure. So that is why we'll go here. Now for assigning the initial stresses, we have to deactivate these clusters. This one, this one, this one, and this one. So there is no building, only the soil, because before the construction of building, the stresses will be initial stresses. So to model these initial stresses, we use Naqeeb model in PLAXIS. So that is why I'll click over here. So according to Naqeeb model, the initial stresses have been assigned. Okay, so update. Now we'll go to the calculate menu. We'll start the calculations. Save soil structure interaction. Now the calculation phase has been started. Okay. Now firstly, the calculation phase will consist of basically two phases. Firstly, we'll analyze the plastic analysis, then we'll run the dynamic analysis. Firstly, we'll go to the static analysis. So for the plastic analysis, we'll go to the parameters. We'll take the additional steps as 250, and the stage construction will define the building. Now we'll have to deselect or deactivate this basement soil material, as we have to define the first phase in the static case. Now we'll select all the plate elements. Yes, this. So here, this is how we can define the first phase. We have to activate this horizontal displacement. So update. Now we'll go to the next phase, and in the next phase we'll select the dynamic analysis. We'll go to the parameters. Here we'll select the reset displacement to 0, because now we don't want the influence of previous calculations. We want the displacement to be 0. It will start from the 0. So that is why we'll select the reset displacement to 0. In the previous videos, we have discussed the undrained condition and these things as well. So we'll give the time interval 10 seconds, because the time interval of earthquake is in seconds, so that is why it will be in second. So iterative procedure will go to the manual setting and will select the dynamic subset to 1, because otherwise it will take a long time. So that is why we'll select it as OK. Now we'll go to the multipliers. We have to assign the earthquake value. So we'll go to this option. Now you can see either if we have the amplitude or frequency or initial phase angle, then we can provide this harmonic load multiplier. We can apply the values. If we don't have, in this case, what we will do is there is inbuilt accelerogram of an earthquake that was given by the USDS, United States Geological Survey Department of earthquake, and that was recorded in 1989. So we'll use that file that is inbuilt. So that is why I'll click load multiplier, will browse, and this file will be in the software inbuilt. So I'll go to the C here. I'll go to the program files where I have my PLAXIS software installation setup. So from program files, I'll go to the PLAXIS. Yes, I will select this one. Now I'll choose that file. This one, 225a.smc file. This SMC file is inbuilt. So this is the data of accelerogram of earthquake recorded by USDS in 1989. So you can now we have to select the acceleration view. So this is the accelerogram or data of that earthquake that was recorded by USDS. So it is inbuilt. So if you have your own, you can put that. So for the time being, I'll click OK. The properties of this earthquake are given over here. Now OK. OK. Now before going to calculation, I will select the points for curve. I want one at the top, one at the bottom, and here. Now update, and we'll start the calculation. Now the calculation phase process is started, and it takes a little bit time. It takes a little bit time to perform the calculation, soil structure analysis. So I hope this video will be helpful for you. It's a basic about the soil structure interaction. So now it will take a little bit time to complete this. You can see here the force in the x direction has been applied, and this is displacement, summation m displacement. So this is the amount of displacement. Now current steps 149, so it will complete 251 steps. So that is why it is taking a time. Maximum iteration it can take 60. So dynamic time is selected as node element A. We can select node B, C, and D as well. So dynamic time is 10 seconds. 10 seconds. So now the calculation process is completed. Now this is OK. We'll go to the output, and you can see the deformed shape of the building. So this is how the building has been displaced from this point to this point. So now if we want, we can estimate or analyze different kind of data, like go to the deformation and horizontal displacement. So horizontal displacement values, this has been displaced from here, horizontal acceleration. So you can see here, this is how the mode has been changed from in this way. So if you know the dynamics, so you can better understand these modes. This is how the building will behave like when the earthquake of the quantity we have given the USGS recorded data. So this is how the building will move. This is the mode of building when the earthquake is given. So this is how we can model the soil structure interaction. Now, if we want to calculate how much displacement has been occurred in the x direction at the top and at the bottom, now we'll go to the table here. Yes, now in the table we want no, these are the coordinates x and y. We'll select the displacement in the x direction, that is maximum. So we'll select the maximum displacement. You can see here there are too many steps. We'll have to manually see how much the maximum amount of displacement has been occurred at the top. So we'll see at 30 there is a displacement of 18 mm, 18 millimeter displacement at y coordinate. At 30.5 meter height there is a displacement of 18.8 millimeter, and we can see at 31.25 there is a displacement of 18.5, and this is how you can analyze that how much displacement has been caused by the earthquake at different position of the building. So you will see at the top at 30.5 meter in the y direction, and it is located in the x direction at 47. So the displacement in the x direction is 18.698. So now if we want to generate the curve, we can go to the curve program. Time displacement curve can be generated. So okay, we'll select the soil structure interaction file, this one. Now displacement here, and we'll select the here we'll select in along the x-axis time, and displacement over here to the point A, dynamic time. Okay, so made the curve, we'll select the different points. Okay, so this is the data of you can see the displacement data with the passage of time at point B. We can add the curves from here, and we can select the C and the UX. Okay, so this is how you can plot the data of the horizontal direction displacement in the horizontal direction for at different points at the base and at the top and at the base of the soil. So I hope you like the video. If you like the video, so please subscribe and share.